72, edit distance. To solve this problem, we need to know one concept, and that's dynamic programming. And that basically is all about breaking down complex problems into simpler subproblems. So let's see this in action. Well, the objective is to turn word 1 into word 2 by either inserting, deleting, or replacing characters. How does that work? Well, just from a face value, to turn word 1 into word 2, we are faced with one of three options: inserting, deleting, or replacing. And then we break it into a problem where we have more of the same decisions. And this tree, as you can see, is going to grow exponentially. And another thing you can notice is, let's say you want to calculate the path to this node. Or let's say actually we want to calculate the path to this node, to this node right here. Well, we're going to calculate the path to that node, we must go through this route. And then to calculate the path to this node, we must go through this route. Notice we are repeating the calculation of this traversal. So is there any way to save whatever that traversal value gives us, like the result here, so that we can use it immediately to determine what subsequent values should be? That's the core idea of DP, not repeating calculations. And more importantly, how does this even break down into the simplest case? And what is the simplest case? Well, the simplest case is simply substituting the same character for the same character. How do you turn A into A? It's 0. How about AB into AB? That's also 0. What about ABC into ABC? That's also 0. So what is the relationship? Well, this problem can be broken down into this problem because C and C are the same. It doesn't take anything to substitute C and C, so we can consider the string without it, which becomes AB. Well, B and B are the same, so we can consider the string without it, which becomes A and A. And A is the base case, right? There's nothing that goes below this. So this is case 3, case 2, case 1. If we want to solve for case 3, we want to break case 3 down into case 2 into case 1, which we know the base case, case 1, to be 0. Hence, by relation, 2 is 0, and by extension, 3 is 0. So that's the idea. And we save these calculations in a 2D array to save on computing. So we're going to clear up some space by deleting this. And we're now going to paste in the table which I've prepared beforehand. And that is going to be our table. So what is this purposely left empty position right here? Well, that just stands for the empty string. And what does each of these positions represent? Well, this position represents HO into R, right? HO into R. What about this position? It's HORS into RO. And therefore, we want to calculate this ultimate position. But we need to calculate this by filling out this array in this order. And that's because by default, we're just going to set nothing into nothing to be 0. And then here, how do we get from nothing to R? We insert R. How about in nothing to RO? We insert 2, 3, and etc. So this, by extension, is the same. So how do you fill out this position? Well, the objective of that position is to tell us, how do we get from H into R? Well, like above, previously, we saw that we have to go through an intermediate step because we're saving prior calculations so that we can use it to derive the new one. And what calculations have we already known? We know, let's just call the original W1 and the target W2. We know how to get from nothing into nothing. And that takes exactly 0 steps. And I'm going to box up the procedure already given to us. We also know the procedure of how to get from, so this is the original, that's the target. How do we get from H into nothing? To get from H into nothing, that takes 1 step. That's given to us. And what about this one right here? Well, that denotes going from nothing into R. And that takes 1 step. So we always start with H. How do we put H into the given calculations so that we can save on compute time? Well, let's consider this case. How do you get from H into the necessary input for the given calculation, which is an empty string? We simply remove H. And what about for this case, case 2? Right? For case 2, it's going to be the output getting into the output of the given calculation into the wanted result, which is R. So we just add R. So in total, we have 1 calculation, 2 calculations. So that's 2. And then 1 calculation, 2 calculations. So that's 2. And what about for the first case? Well, the upper left diagonal to its lower right diagonal represents a substitution calculation. And that makes sense, right? Because this represents from H to R. We already considered the case of adding a character and subtracting a character. What's left is replacing a character. So obviously this diagonal, well, just from logic's sake, like that should be the only thing left. And indeed, it makes sense. To get from H to R, we just simply go here to do +1. And we could have went the route like this, right? To get, well, the route of 2 and 3 doesn't really work here, because if you go here, you have to remove H, and then here you have to add R, right? That gives 2, but that doesn't really make sense because substitution takes only 1 step. So what you can think of this nothing to nothing can be like that brief moment, like while I'm substituting H into R, for a brief second, like it becomes nothing, and then it becomes R again. But that's the only way like this pattern holds. So you can think of it like that for the sake of understanding. So this becomes H to R in just 1 move. So which of these paths gives us the fewest number of substitutions or calculations? Well, it's just this step, right? We just do one substitution, so this is just 1. And we repeat this calculation over and over again. And you see why we need to do it when you fill out the column in this manner before we reach the target here. Because filling out each position requires us to know its neighbors right here. Hence, if we wanted to know what this is, which is the answer, we need to know the values here. So that's the idea, and that is what we're going to program up in Python. So as we said, let's see, we're going to say the number of rows is going to be the length of word 1, and the number of columns is going to be the length of word 2. And you can swap this, but it makes no difference. And we're going to initialize a 2D array called dp, where it's going to be in the inside 0 times for underscore in range calls plus 1. That sets the number of columns, and then on the outside for underscore in range of the rows plus 1. So this creates a dp array that we saw in the example. And how do we now initialize it? Well, the row 0 and column 0 is going to be initialized very easily. There's going to be 4i in range, right, of rows plus 1, and dp of ij is going to be equal to I, or rather dp of I0. And the same thing goes for the column, where it's going to be 0i, like so, and that's going to be columns. And with that, that should be good. So we initialized the dp correctly. And how do we go about populating the body of that 2D array? Well, we know that for every position, it's the minimum of its upper left 3 neighbors. So for I in range of 1 to rows plus 1, remember, we're not starting at 0 because we don't need to calculate 0. We're not populating that. So for j in range of 1 to calls plus 1, the current dp position, dp of ij, is going to equal the min of the upper 3 neighbors plus 1. And the upper 3 neighbors are dp of I minus 1j. And then what's the other neighbors? Well, it's going to be dp of I, j minus 1, and dp of I minus 1, j minus 1, plus 1. And with that, once we calculate everything, we just return dp of rows and dp of columns, which we return like so. But this is not okay, right? We have to first check, right? If the value at word 1 of I is not equal to the element at word 2, so word 2, j, and we put a not in front of it, then we must execute this statement. But if it is the same, right, it goes back to the example, right, AB and AB. AB and AB is the same as considering A and A. It's simply the value stored in the upper left neighbor. We don't even need to consider it. Else, dp of ij is just equal to dp of I minus 1 and j minus 1. So there we go. That's the complete logic. So if you run it, it should work. And invalid syntax. So we initialized this wrong, and I forget exactly the syntax. So I'll be right back and I'll fix this. Okay, so it turns out I shouldn't have put the multiplication sign in front. Quick syntax error. My bad on that. So this should work now, so let's run it. And this does not work. String index out of range. Oh, this should be I minus 1 because this goes all the way up to rows, and there's only rows minus 1 values. So yeah, so that should work. There we go. Let's submit. And that's the solution.